Welcome everybody. Today we're going to talk about central limit theorem, CLT for short, and it tells us that we get Gaussian normal distribution, this bell shape, from this shape, or actually any other shape that you can think of. And how is that possible? And you can pause the video and read the definition, but from my experience people usually don't understand CLT just by reading the definition. So let's jump straight to an example. Imagine that you are a student and you're attending a math class with 300 other students, and your professor tells you that you live in a city with 100,000 people and average yearly income of them is around $64,000, okay? And he wants every one of his students to test if this value is a true value. So every one of his 300 students has to randomly choose 100 people from Tulsa, call each one of them and ask how much they earn, and take the average of their values. And they should get the value around $64,000. Because if they would call one person, they could call a lawyer that earns $200,000 or a cleaning lady that earns $25,000. But if they choose 100 people randomly, they should get all the variety of earnings. So the average value should be around 64, the real average value in Tulsa. And let's see how the distribution of these 300 values looks like. And it looks like this. We can see a bell shape from this shape, okay? And it's not weird. Remember, the key to understand it is the average value of a sample of 100 people in this case. So if you take 100 people from this distribution, the average value of them should be close to the real average value of a population. That's why the distribution is close to this mean, to this red line, okay? And I just want to be sure that everybody understands this graph. This graph is the same as this, just we limit the x-axis. So from those 300 students, 2% of them, which means 6, reported the average earnings of 100 people that they called from $54,000 to $55,000. And everybody can read in the same way. Okay? So we see that those values are close to $64,000, but they have some standard deviation, the variation. So this is an example when we can use CLT. So let's imagine that the mayor of the city thought of the idea of a lottery, that he will choose randomly 100 people and he will give them their yearly incomes in this lottery if they will be chosen. So he says, I have $7 million left from this year, so we can do this lottery. But what is the chances that this $7 million will be too little for those people? If we have 5% chance that this will be too small amount of money, I don't want to do this lottery. And we can use this CLT to calculate it, because average earnings are $64,000, so 100 people would earn 6.4 million. But we can easily see that this average is not written in stone. It's not a sure thing. We have some standard deviation. So from looking at this graph, we can see that there is more than a 5% chances that he will choose a random 100 people that will require more than $7 million. Okay? And I will do another video of how to use CLT with examples. With this example, we will actually calculate it using formulas. But this is just to show you that we can use this CLT. And it works for all the cases. So here we have a case of rolling dice. So you literally throw a dice 100,000 times, and this is a distribution, so you're equally probable to choose 1, 2, 3, 4, and 5, and so on. And this is the distribution of average value of a dice in 200 rows. So you throw it 200 times, and you have 5, 3, 4, 4, 2, 6, 1, and so on, 200 times. The average is supposed to be close to 3.5. And that's why the distribution looks like this. In the last example, you have a hockey camp with 2,000 teachers, average 175 centimeters of height, and 8,000 kids with the average height 100 centimeters. Okay? And you get this distribution, and even from that distribution, you have the average height of random 100 people, so the sample, normally distributed. Because if you choose 100 people randomly from that, it would be probably around 20 teachers and 80 kids. So the average value would be around 115. Not weird thing. It's supposed to be like that. Now we will see how the shape of distribution depends on a sample size. Here we have a slider that we can manipulate how many items we take to a sample. Here we can manipulate how many samples do we want to take. So in a sample is 30 items, and we have 300 samples and distribution of them. And this normal distribution of sample means doesn't always looks normal. It depends what sample size we get. The commonly known threshold when you can start to use CLM is sample size of 30 or more. Okay? When you have that many samples, the distribution looks a lot like normal distribution. But remember, it's not written in stone. It's like this 2,000 calorie diet. For a small woman, it would be way more than she needs. For a sumo guy, that would be just a starvation. So don't treat it like a sure thing. For particular cases, you will have to go higher than 30. Okay, what is happening if we have a smaller sample? How the distribution looks like? The distribution looks like a mix between this distribution of a population, and normal distribution. And you will see that in a moment. Let's take the smallest sample we can get, 1 person. Okay, so we have 300 samples of 1 person. And it looks exactly like this distribution up here. And it's not something weird. It's supposed to be like that, because we're literally taking 1 person from all over the place. What will happen? Try to guess what will happen if you will take 2 people. Okay? We get something like this. And what happened here? We have 3 peaks. Maybe some of you know why. Here we have an example of choosing 2 teachers to that sample. Here we have an example of choosing teacher and a student. And here we have an example of choosing 2 kids. Okay? And we have possibilities. What is the probability of choosing each variation? So in the first case, when we have a sample 1, there would be 80% for kids and 20% for a teacher. But now we either choose 2 kids, would be 4/5, so 80% squared, it's 64%. Kid and a teacher and a kid, so 32%, or 2 teachers. Okay? What we can already see is that the least probable values, the least probable peak, practically disappeared. It's a fraction of what it was before. It's exactly 20% of it was before. And here we have a decrease from 80% to 64%, much less. It's a simple statistic, simple math. The smaller percentage will drop more quickly. So let's see what distribution we'll get when we get 3, sample size of 3. And we have 4 peaks, 3 teachers, 2 teachers and a kid, 2 kids and a teacher, 3 kids. Okay? We could do this calculation all over again. We would have 3 kids, kid and 2 teachers, teacher, kid, teacher. You have to remember that in a way, the order of them counts here. Okay? But to choose a teacher 3 times in a row would be 1/5 to the power of 3, which would be 1 case in 125. And choosing a kid again would be 4/5 to the 3rd, which would be, I don't even know, what is the value? I think around 50%. So it doesn't decrease that much. It's still pretty visible, and this one is barely visible. And if we would go further and further, more size of a sample, we would be losing this distribution, it would not look like this distribution anymore, and it would get closer to the average. And we start to see the shape of normal distribution slowly, okay? And if we would go 15, we'd see it much clearly, because those values usually farther away from the mean, will disappear much more quickly. And they would be shifted, the mass would shift more aggressively to the mean than in this case, okay? And here we can see pretty symmetric shape, okay? The symmetric shape starts to be visible. And now we get this magic value of 30, and we have something similar to a normal distribution. Now we can play with this slider and see that it looks pretty much like a normal distribution if you have a bigger sample size. If we would get again to very small sample sizes like 13, it would be granulated. It's not that smooth. You still can see the peaks that were very visible at very low values, like here. And we can see the same with rolling dices. Okay, so we will take few small samples to see what is happening. If we take a sample of 1, we see something very similar to what is here. Maybe if we take a number of samples of 1,000, so we see basically the same distribution that up here. If you would take 2, we can see a shift. It's getting closer to normal distribution. Actually, in this case, it's getting close pretty fast. And what is happening right here? And we have an explanation here. If you're choosing what is the chances of getting 1, 2, 3, 4, 5, 6? In all the cases, 1 in 6. Okay, so it's the same chances of getting 3 and 6. No big deal. What is the chances of getting average of 2 rolling equal to 6, and what is the chance of getting 3? And we have to look at this. Here we have all the combination, all 36 possible combination to get a number. And only one of those, 6 and 6, give you an average equal to 6. And 5 of those give you an average value of 3. And you can see that the value of 3 is approximately 5 times bigger than the value of 6. And the other way that you can look at it is if you pick a 6, there is nothing that would push the average to the right. And there is everything to push the value to the left and push the value strongly. So if you would choose one, it would push it right here. Okay? And if you have 3, you have a lot of things that will pull you left and a lot of things to choose as a second part of a sample to pull you right. So you would stay in the middle. Like this distribution would not get smaller that fast. It wouldn't approach this average value of 3.5 so fast. Let's roll a dice 3 times. And we can see that the value of 6, you would have one chance into 216. So this value should be non-existing in a moment if you would keep pushing the sample size to a bigger value. But 3 is still existing. It will slowly be shifted up to the 3.5, but it's not so rapid. Okay? So let's take a value of 5. And we can start to even see the shape, not the V shape, but this actual shape of a bell. Let's take this value of 30. And we see something very similar to a bell. Let's take a value of 100 to see it very clearly. Yeah, and here we have a bell. And here we have a proof that the expected value of a sample mean is the expected value of the population. So expected value of a sample, this distribution, should be the same as expected value of the population. And for people who would like to see a derivation of this expected value of the mean, if we add all the values in the sample and the expected value of every single sample is the expected value of the population, then we just simply have n of the same values. And what we do in a sample, we divide it by number of items. So they would cancel out and we would get x, but you probably already suspected that. And just in case, I would like to remind everybody of what the expected value really means. So expected value is the sum of the values of items in a distribution multiplied by the probability of those items to appear. But in this case, in most of the cases in CLT, the probability of every items to be chosen is the same. So we can make this formula simpler by calculating this average, this formula. So we add every single item and we divide it by number of items. So in this case, we add every single height of kids and teachers and divide it by number of kids and teachers. And we have average of 150. But there's another way of looking, more visual way of looking at mean of expected value. Is this, the fulcrum, point of support. You would simply put this distribution, shape of this distribution on this point, it would be in perfect balance. It wouldn't shift to the left or to the right. Just like those swings that you sometimes have at playgrounds. This is this fulcrum. And if the people of the same weight would sit here, they would be in perfect balance. But they are not always at the same weight. If we would have heavier person here and smaller person here, we would have to shift this fulcrum here, this point of support. Then they would be in perfect balance. So I'd just like to remind you that the mean is not always in the center of the distribution. Sometimes it is, like in this case, but not always. And remember, expected value, it's not the value that you would most likely choose from all of the items. It's the average value. So you add everything up, you divide it by number of items. If the probability of picking each item is the same, if it's not, you have to use this formula. Or you could just simply look at the shape and where you would put the fulcrum for it to be in a perfect balance. So now you have a basic understanding of what CLT is, and here you have the most important things to remember. But it's not everything that we can know about CLT. And in next videos, we will talk about standard deviation of sample means. So how wide would be that graph of sample means? What would be standard deviation of it? And where we can use CLT in real life with examples and with calculations. And to understand that, we will have to, I will explain to you p-value, those distributions, hypothesis testing. And it seems like a lot of things, but they are very similar and connected with each other, so it won't be that difficult to learn. And this video is available right now, and these videos I hope to upload within a week. So if you want to continue learning, go now to this video and learn.